Let's start with a set of examples now. An LC circuit has a 10 milliohm inductor. L equals 10 times 10 to the minus 3 henries. A 10 millihenry inductor. The current has reached its maximum value at 0.60 amps. And that happens at t equals 0 seconds. A short time later, the capacitor reaches its maximum potential difference of 60 volts. What is the value of the capacitance? What is C? So let's start with how are we going to try to figure out C? Well, we know that capacitance C is charge divided by potential. So the maximum charge divided by the maximum potential difference. Okay, delta V max is fine. What about QO? Well, we don't know QO, but we do know something about the current. We know that IO, which is given by omega times QO, where omega is 1 over root LC. This means we can solve this expression for QO in terms of IO. QO equals IO times the square root of LC. If we put this expression in this expression, then we should be able to solve for our C. So let's try that. So C is Q over delta V maximum, QO over delta V maximum. QO is IO times the square root of LC over delta V maximum. If we square both sides, we get C squared is IO squared LC divided by delta V maximum squared. Double check, I didn't lose any squared signs. Divide both sides by C, cancel that squared. That gives us that C equals IO squared L over delta V maximum squared. 0.60 amps squared times 10 to the minus 3 henries divided by 60 volts squared gives us 1.0 times 10 to the minus 6 farads, or 1 microfarad. Okay, so that's our first example. For another example, let's say that for your final exam in electronics, you have to build an LC circuit that oscillates at 10 kilohertz. So careful here, 10 kilohertz is the frequency, not the angular frequency. So F equals 10 times 10 to the 3 hertz. We'll put in brackets omega equals 2 pi F. In addition, the maximum current must be 0.10 amps. And the maximum energy stored in the capacitor has to be 1 times 10 to the minus 5 joules. I call that E maximum. What are the values of inductance and capacitance that you have to use in this system? So let's just remember for a moment how energy works in an LC circuit. Energy can be all in the inductor, so we can have all of the energy stored in a magnetic field. So for an LC circuit, energy can be U maximum of the magnetic field when all of the energy is stored in the inductor, or it can be total potential energy of an electric field when all of the energy is stored in the capacitor, or it could be a mix of both. So the maximum energy of the inductor would be this value, the maximum energy of the capacitor is this value, and if the energy was split between them, then the sum of those two energies, the mix, would give us this value because energy is conserved. This is just like the maximum, this is just like energy of a spring. Sometimes it's all in kinetic, sometimes it's all in potential, and sometimes it's in both. So let's start by thinking about the maximum potential energy stored in the conductor. So let's start with the inductor part. So U max of the inductor. That's given by 1/2 L times maximum current squared. And our maximum current has a symbol of I-O. So that means that our inductance then is 2 times U maximum divided by I-O squared. We can put in our numbers. We remember that U maximum is the same as E maximum. So that just means that all of the energy is stored in the magnetic field in the inductor. 2 times 1 times 10 to the minus 5 joules divided by I-O squared. Our I-O was 0.10 amps. Gives us an inductance of 0.0020 henries. Or you could say 2 millihenries if you prefer. Okay, so there's our inductance done. What about our capacitance? So let's come back to the idea that we know what omega is, or we can find it pretty easy. We also know that omega is 1 over the square root of LC. So omega is 2 pi f, and it's 1 over the square root of L times C. We know F, we know L, so we can find C. 4 pi squared f squared, we'll square both sides, is 1 over LC. C is equal to 1 over L times 4 pi squared f squared equals 0.002 times 4 times pi squared times f squared. And that's all divided by 1. Okay, I sacrificed my units here for space. Gives us 1.27 times 10 to the minus 7 farads, or you could say 0.127 microfarads if you prefer. Okay, one last example we'll work through. And this one might stretch your brain a little bit conceptually, which is probably what makes it a kind of a good example to do. So a 300 microfarad capacitor in the figure is initially charged to 100 volts. It's going to be the maximum potential. The 1200 microfarad capacitor is uncharged and the switches are both open. What is the maximum value to which you can charge the 1200 microfarad capacitor by the proper opening and closing of the two switches? And then this is the part that might be a little tougher to think about. What even is the proper opening and closing of the two switches? Okay, let's deal with the top part first. What is the maximum voltage that we can have on the second capacitor? Well, the way we can get a maximum voltage here is if we take all of the energy on this capacitor and transfer it to this capacitor. And the mechanism of that happening, and that's what we're going to talk about in this part, is the energy here will first transfer to the inductor. Then it'll transfer from the inductor to the capacitor. So let's find the energy of the capacitor C1. So the total maximum potential energy of C1, I'm going to call that U1, is a half times C1 times delta V1 squared. This is the maximum potential difference on C1. So that's a half times 300 microfarads times 100 volts. That has to be squared. That gives us a total energy of 1.5 joules. Okay, then what we're going to do is we're going to transfer that energy to C2. So U2 is 1/2 C2 delta V2 squared. This time we're trying to find delta V2. Delta V2 is 2 times U2 divided by C2, and then we have to take the square root. Remember that U2, all of the energy has been transferred, so U2 is 1.5 joules. So square root of 2 times 1.5 joules divided by the capacitance, 1200 microfarads, gives us a potential difference, a maximum possible potential difference of 50 volts. And that assumes no energy loss to the wires itself. Okay, so now the slightly tougher part. What do we mean by the proper opening and closing of the two switches? So let's think about what happens in the system. First thing we're going to do is we're going to close switch 1 at t equals 0. So that'll be our first step. So what happens when we close switch 1? Well, the current and the charge on the capacitor plate of C1 are going to oscillate with period T1. Okay, and T1 is a number we can figure out. At a quarter T1, the charge on the capacitor plate C1 is going to be 0, and the current is going to be a maximum. So then at a quarter T1, when the current is a maximum, what we can do is we can open up switch 1 because the current is a maximum, and we can close switch 2. Then the current and charge of capacitor C2 are going to oscillate with period T2, and the current from that inductor is going to start to charge C2. C2 is going to get fully charged at a quarter of a period T2. Then we'll flip open that switch S2, and that will keep it charged. Okay, so we close switch S1 at time t equals 0. So we close this at t equals 0. Then that lets this start to discharge and current flows. Okay, so current flows. It's a maximum at 1/4 T1. Then what we do is we're going to open switch S1 back up at a quarter T1 because the current is a maximum. So open S1 at t equals 1/4 T1. We can find that value. So 1/4 T1 equals 1/4 times 2 pi over omega 1 equals 1/4 times 2 pi times the square root of L times C1 equals 0.063 seconds. Okay, so that's when the current through the inductor is a maximum. So we're going to open it back up at 1/4 T1. The current here is a maximum. Because the current is a maximum, if we open up this switch and close this one, the current will start to flow in this branch of the circuit. So step 3, close S2. So we let current flow S2 at the same time. .063 seconds. Okay, so now we close this guy at a quarter T1. That allows the current to flow. If the current is flowing, it's charging up capacitor C2. We want to open up this switch again when the capacitor is fully charged, because that's when it'll have the maximum voltage. So open S2 at a quarter of a period, T2, so the period for this circuit, at a quarter T2 after it was closed. Okay, and a quarter T2 is a number we can find. So this is equal to 1/4 times 2 pi over omega 2, which is 1/4 times 2 pi times, oh hang on, the phone is ringing. There, I think I made it stop. 1/4 times 2 pi times the square root of L times C2, which is 0.125 seconds. So switch S2 is opened up again so that current stops flowing because the capacitor is fully charged. That's opened up 0.125 seconds after 0.063 seconds. So that's at a time of 0.063 seconds plus 0.125 seconds equals 0.1875 seconds. So that's when that flip switch is flipped back open. So we close this at 0, we open it at 0.063. At exactly the same time we close this one and we open it back up at 0.1875. That's how we let all the energy transfer to C2.